Cool. So before I jump to the presentation, I would like to just talk about briefly about Deeplite. So Deeplite is a deep tech startup based in Canada and headquartered in Montreal, but we have office in Toronto. And basically at Deeplite, we are trying to help companies to make their deep learning models faster, smaller, and more power efficient to run these models on the edge. That's basically the mission at Deeplite. And basically the story back to like 2017 when I basically quit my job and joined Tandem Launch, is a kind of the incubator in Montreal, and I met my co-founder there. So before I jump to more details, let's give me a opportunity to discuss about the background on why deep learning is very important right now, and why deep learning on the edge even is more important than GPUs. So we have heard a lot about deep learning these days, and we know that deep learning drives AI right now. And the reason that it happens is because of two main, I would say, features for deep learning. Is one is the automated features extraction, and the scaling improves performance, very well when you have more data. So we haven't seen this kind of beautiful uh, features in the past with the classical machine learning techniques. That's why right now, no matter what, when we have more data, more power, we can have a better and more accurate models. And we have seen that very well in the NLP field as well. But the problem with deep learning right now is deep learning models, if they want to beat human level performance, they need billions of parameters. And when you have billions of parameters, it becomes super hard to train these models. That's why right now, deep learning with a good accuracy of performance somehow dominated by big companies because they have lots of data and they have lots of compute power. For example, one of these big NLP models, if you want to train that, it costs like 10 or 12 million dollars because you have to run these GPUs and you have to do it, but it gives you very good performance. So that's basically the problem with deep learning. But if you look at the deep learning problem, the problem comes from two parts, training and inference. When we talk about training, it means you train your network. And when we talk about the inference, it's more about how long it takes for you to run it on the hardware. On the training side as well, we have the issues, and also on the inference side. That's a very famous chart from OpenAI team that they show that from 2013 and 2019, which is not up to date right now, the size of the models, it increased by like 300,000x in terms of the number of parameters in the model. But based on the Moore's law, we have a kind of the limit on the hardware side, and we have seen like 10x increase in the number of transistors or in these kind of cores in GPUs. As you can see here, there is no any correlation between these two numbers, and that's why it becomes a huge problem for the industry to train these models and run these models. So at Deeplite, we are focusing on inference. So basically, we assume that we train the network, and now it's the time to run it on the hardware. It's going to be in GPU, CPU, edge, and any sort of hardware. But as a part of our mission, we are trying to unlock this opportunity for people to run these models on the edge devices. And the reason is, right now we have a very good models in deep learning, and people, they have been solving these problems with deep learning. And right now we have a good models with good performance. But the issue is, it's very hard to deliver these models to the end user. And if you want to do it, the options right now is either to use powerful GPUs or use cloud services. And if you want to run it on a laptop CPU, even on like a Raspberry Pi, it's almost impossible, or it's super slow. That's basically our goal here, to unlock this opportunity and use the commodity hardwares like ARM CPU and Raspberry Pi, ARM CPU on the phones or on laptops like Intel CPUs to run these models. So if you want to talk about more on edge challenges or edge computing challenges, we can see there's three different problems. These models requires lots of computational complexity. For example, if you want to run a very simple classification model, you may need like 2 billions of floating point operations, just multiplication. The other problem is the memory footprint. These models, because they usually have lots of parameters in the model, they are big, very big. For example, it's like 100 megabytes or 200 megabytes, just parameters, just floating points. And you can see that if your Raspberry Pi only has like, I don't know, 200 megabyte fast memory, it's going to be very hard to fit everything on the chip memory. And the other problem is the power consumption. When we have lots of floating point multiplication, when we have lots of parameters that you need to store on the memory, of course, you have lots of memory transfer, which drains your battery by heart and very, very fast. So there are some studies that, for example, right now, if you want to use this kind of hardwares on the car, for example, on Tesla, and you want to run these kind of models, it drains your battery like 20% of your battery, just these hardwares. 20% of the car battery it's a huge deal. And also they're super expensive. Right now, if they are using some sort of Tesla high-end GPUs, and each costs you around $10,000. So imagine you're using three of them, like $30,000 just for GPUs, and the car like maybe costs you like $50,000. So the right now it doesn't make sense to use these kind of models on even cars, but that's basically the issue that we are facing on the edge devices. That's why people right now they are trying to run their model again, either on the cloud or just rely on the local high-end GPUs. That's basically for regular object detection, segmentation, or computer vision models. If you want to work with more sophisticated models, they're going to be even more, slower or heavy for your hardware. So that's basically the problem right now in the market, and there's a huge problem. And that's basically the place that Deeplite tries to help companies. Our stack basically consists of two parts. We call it Deeplite Neutrino and Deeplite RT, or Deeplite Runtime, or DLRT. And the reason that we have it in the two pieces is to basically optimize neural networks in the best way. So imagine you have the first level that you train your network. It's going to be like TensorFlow or PyTorch. Then you can use, I'm going to explain it a bit in more details. You can use Deeplite Neutrino to reduce lots of parameters from the network to make it lighter, basically. So at this stage, we can compress it by heart a lot. For example, from this 80 megabyte to 2 megabyte, it's a real number, for example. And then after you compress the network, you remove lots of parameters from the network while you maintain the accuracy. The next step in the Deeplite stack is to use low bit precision to represent the model, like 2 bits, 1 bit, 4 bit. And if you imagine use 2-bit precision, you can have another like 15 or 16x reduction in size, because right now everything is 32 bits. When you present every weight in 2 bits, so it means you have like around 16x reduction in size, and also it makes it better to run on CPU. But you need to have your own runtime to run it in 2 bits, because all the runtimes or compilers, they accept that everything is floating point 32. And if you want to make it like 2 bits, you need to change the way that people actually doing the convolution or fully counted layers or gem operations on the real runtime or compiler. So basically, right now we have lots of good demand for both of this, and Deeplite runtime is almost there. It's in the development phase, and we have seen very, very good results on embedded devices like Raspberry Pi, Jetson Nano, Jetson TX1, TX2, these kind of boards. And the combination of these two levels, the compression, it gives you a very high compression rate, and which helps you to fit your model on the device, on memory. That's very important to do that. So as I just shown here, the focus for us is here. Of course, this one is very important, but that's the biggest item. The reason is, on embedded devices or edge devices, 80 or 90% of the power consumption or the latency goes to memory transfer. And if you want to go like a DDR or these auxiliary SD cards, it kills your performance by heart. That's why we want to keep our parameters or our data next to the edge of compute. That's basically the motivation behind all these compression techniques, low bit precision techniques, to make sure that we can compress the network, that we can bring the model or the parameters very close to the edge of compute or ALU here. And by this, we can, eliminate lots of redundancy and, unnecessarily memory transfer. So that's basically the whole goal behind all these techniques. And I don't want to emphasize more how slower this kind of level of storage. You can see the numbers. It's like from this one to this one is like order of magnitude. From this one to this one is like a 2 or 3 order of magnitudes. That you see the the speed is very, very slow here. So I'm going to explain a bit, in more details how our technique works. So the first step, I'm going to talk about this level for now, and then we can jump to the low bit precision. So this one is a very standard like VG architecture. VGG is like a classification model, and for the classification model, basically the idea is if you have a picture, you can classify it and put a tag on that picture. Of course, we can extend these techniques to other models like object detection models, segmentation model, and more sophisticated models. But for the purpose of this presentation, I've used VGG architecture because it's very simple and it's easy to explain that. So that's a real classification model. And as you can see here, we have different layers, and they are basically convolutional layers, which 90% of all these computation goes to convolution layers in CNN-based models. That's why we are tackling these layers to optimize neural networks. But the way that it works, so I just change it to this way to make it even simpler to understand. So we have different layers here. As you can see, we have first convolution layer. It has like 3 by 3 kernel, 64 no, and we have different layers here. As you can see, each layer stores lots of parameters, a lot. So we are using one technique here, and we call it network within network. And basically what we do, we replace one layer, which is a very fat and big model with lots of parameters, with a much smaller one, but thinner network. These are the real numbers. For example, this layer has 2.3 megabytes of parameters. But when we replace it with this tiny, thinner network, the number of parameters that you really want to store is like around 140 kilobytes. But it doesn't really impact on your network, on the accuracy a lot. That's basically one intuition here. Replacing layers with a smaller, thinner layers, and you can reduce lots of parameters. So you can apply this technique on the different layers. You can apply it here, you can apply it here. But the biggest question here is where to apply this technique. Because if you just apply it like blindly, it really ruins your accuracy by heart. So that's the one challenge here, to select which layer you want to apply it. The second question here is, what's going to be the transformation, basically equation here. You can replace this layer with like just only 2 layers, 3 layers, 4 layers, 5 layers. And of course, if you have a bigger network here, you can obtain better accuracy. But if you're using a bigger network here, the size reduction is not going to be that high. That's why you need to find the sweet spot, how much you can press this network and you can get the best accuracy out of it. That's another challenge with this technique. And the other challenge is, imagine you find your network, and imagine you find your transformation equation. Now the question is, how do you want to minimize the error when you approximate this layer with this smaller, thinner layer or network? That's the third challenge. So basically, at Deeplite, we kind of overcome these challenges, and we have some sort of working solution, even in production, that it works very well. So before I jump to other, maybe it's better to just jump here. Um, yeah, basically these are the steps that we are taking here. First, you need to have a layer selection, but you can't just do it brute force or like a randomly, because the space is very huge and you need to do lots of trial and error. And the problem with neural networks is you cannot do the trial and error, because every changes that you make in the network, the accuracy drops and you cannot rely on that accuracy anymore. And you need to retrain the network to gain the accuracy. And this one is a very, very time consuming process, which doesn't let you do this brute force search. That's the first step. So one of the techniques that we are doing here, that we are using some sort of learning to learn which layers we want to touch. If I come back here, so basically the idea here is we are using some sort of mask that you put it on each layer. And during the training, you can play with these masks. And then you can mask some of these layers, or you just unmask some of these layers. While you are doing this, you train your network and you train your mask as well. And somehow you figured out by masking these layers, you can still get a good accuracy while you can replace these layers. That's basically the learning approach for the first step. And the second step is the transformation function. I just mentioned that. So you can use like 3 layers, 4 layers, even the bigger layers for each transformation. I just put the equations for the two samples. Like if you want to transfer your convolution layer with 4 layers or with 3 layers, you can do that. You can do it for, with 10 layers. It's not something that it's hard coded. But these two slides just shows like four layers or 3 layers. So basically the idea here is for the 4D tensor like this, we can always approximate it with this formula. But the biggest, I would say, or we need to be careful about the input and output of the shapes for each layer. I think that's the biggest hint here. For example, here, we need to preserve the input and output shape of this layer. And the reason is, if we want to change the input shape and output shape, we change the whole dynamic of the network, and then it becomes a totally different network. It behaves totally differently. That's why it's super important to keep the shape, which it will keep the whole dynamic of the network. And it happens in both scenarios here that I just put the dimensions. As you can see, if you can see the R, you can transform your 4D tensor to this one. And the first one and the last one, basically, as you can see here, it transforms your convolution. And then at the last one, it returns it back to the same size. It's its original size. And this is the original size for the first one. So that's the second step, that we can transform these layers. And then the other question, which is also important, we have another learning steps to learn the size for each inner layer. Imagine here we just talked about the network, but as I can show you, you can see R3, R4. These are the numbers that you can play with. So lower size is always better, because you can have more compression rate, but more compression rate means losing more accuracy on your network. Again, you need to find the sweet spot here. What's going to be the best number that you can use? I would say that's the most difficult part of this process, to find that. And again, you cannot use trial and error or brute force solutions here. But again, it's another kind of the learning approach in our technique, that we learn these kind of numbers with one retraining to learn what kind of the size we can use for each layer to maintain the accuracy. And at the end, you need to approximate this inner layer, this layer with this layer. So basically, you need to replace this one here, but you need to transfer these parameters from this layer to this one. So we use knowledge distillation as a part of this process. However, we also need to minimize the loss. If you look at this one and this one as a kind of the optimization problem, you can lower the loss and make sure that you have a almost similar functionality from this layer and this layer. They're going to be totally different, but the behaviors, the behaviors are the same. So long story short, after we apply these techniques, you can compress your network. I put some numbers here. So these are the real numbers from different kind of, models, from the image classification to object detection segmentation. Most of them are, or all of them are, open source models and data sets to make sure that everybody can access these kind of models and try that. Of course, different models have a different type of metrics or evaluation metrics, from top one for image classification to MAP for object detection, or MIOU for segmentation. As you can see here, we can see different compression rate for different models, and it is totally accepted because, for example, VGG has a huge or lots of capacity to learn, and this one is a small data set. So you don't really need that much capacity. You can, it's like a sponge. You can squeeze it and just keep the essential data in your network. But on the other hand, ImageNet is a very big data set. Of course, ResNet-50 is also a very huge model, but you need lots of capacity to learn those features on ImageNet. That's why you cannot squeeze this sponge a lot. But for the market, that's a huge reduction in size for that particular use case. So that's basically the numbers that we have seen, and we validated those numbers with market, and these are very appealing numbers even for industry. So one of the as a side effect, one of the things that we have found, and which is again very, very important for the companies, that we found that why we want to go with a smaller network at the first place, why we can't train a bigger network and then compress that network. So basically, for example, here, these are the models on the ImageNet. ResNet-18, so I've sorted them based on size and number of parameters. As you can see here, these are the number of size, and that's the top one accuracy, and also the number of parameters and number of the MAC, basically to represent the complexity of the network. So if you have a bigger network, it's always easier to train that, and you get a better accuracy. But if you use a smaller network, you can get a better accuracy. For example, ResNet-50, the original ResNet-50 gives you around 7% more accuracy than ResNet-18 on ImageNet. But of course, it's bigger, it has more MACs, it has more parameters. Same thing for a C400 dataset. But what we have seen, which is very, very interesting and very, very appealing for the market as well, that why you can't just use ResNet-50 to train your model on ImageNet and then just compress that network. As a result, you will end up with even a smaller network comparing to ResNet-18, less parameters comparing to ResNet-18, less computation again comparing to ResNet-18, but way more accuracy. 5% on ImageNet is huge for this kind of models. We have seen that again in the different datasets like C400. And also we have seen it on the other dataset. It's an object detection model on the VOC dataset. YOLO V3 is one of the state of the art, but not right now. It's like a YOLO V5, but YOLO family, they are well known for the performance, but they're very huge, like 235 megabytes. On the other hand, we have the one of the most compact handcrafted model, like MobileNet V2 SSD Lite. So you can see the size. You can compare the size. However, you cannot compare the accuracy or MAP here. But it is hard to train these networks because they're small, and sometimes you need some sort of hyperparameter tuning to train these networks. But what we have seen, we just took YOLO V3, we just compressed that model to meet this delta. And again, we could achieve that, and we could achieve almost similar size here, which is very, again, appealing and interesting for us to see. As a part of this tool, I didn't explain that a lot. You can also specify delta, how much delta you want to see in the accuracy drop. For example, you can go from 1% to 50%. That's why in this scenario, we use 15% or 0.15% accuracy drop in MAP. You can use it like 0.01, 0.02. It's up to you, but we just wanted to meet this accuracy. So long story short, that's the one thing that we can definitely encourage people to use. Instead of going to the small network, just use whatever you want and then compress that, and you can achieve a very good accuracy, even higher accuracy. Another side effect of compression that we have seen, it is very, very interesting, that when you have a compressed network, it works like a regularization. You can see better generalizability in the network. So our compact networks usually performs better on the unseen data than the original network, and it's basically some sort of the information theory, because you just keep the uh, you know right information or important information, and you remove the redundancy, and it helps you to have a more generalized network for your task, which is also very important for the market and even for the academia. So that's basically the part of the first step, which is the compression, to remove lots of parameters. You can see from here to here, from 60 mega or millions parameters to like just 3 million parameters as a first step, which reduce a lot on the memory transfer. And the second step is like a low bit mix precision that we are working on that. And the goal here is to compress or optimize even more. And the reason that we are going with the low bit precision is these hardwares or the runtimes, they only accept a floating point 32. Some of them, they accept like INT8 or FP16, and that's it. And if you want to go lower than that, you need to find a way somehow to run these models, because 8 bits is the limit for the hardwares. Some of them even all works with 16 bit. Some hardwares recently, they support 4 bits, but the data path usually is 8 bit for the computer architectures. Going lower than that, you need some specific requirements for your runtime to do it. Otherwise, if you just want to use padding, you can't gain any speed up or anything here. But as a very early numbers that we have seen on our DLRT, basically we put the like TensorFlow Lite integer 8 as one of the most, I would like, popular tools in the industry as like a baseline. We have seen some very good speed up on CPU, and these are kind of the outdated numbers. We have seen even higher numbers in terms of speed up, and while we could maintain the accuracy. So basically combining the first step and the second step can give us even more accuracy. These numbers, sorry, more performance. These numbers are only about low bit precision. We didn't include any neutrino optimization results here. So adding neutrino and this low bit precision optimization, it gives us even more performance on the hardware. So right now the focus for us is ARM CPU, mostly Cortex-A series. In terms of the models, it's mostly computer vision CNN-based models. The framework that we are using right now is PyTorch. So we are focusing PyTorch, but later we want to support TensorFlow. And at the end of the day, the tool is going to be an automated tool that people can easily use it and just optimizing their models. Right now, if you go to our website, you can access the community version on GitHub. So it is, sorry, it is available publicly. So you can install it, you can play with that, you can compress your networks. Of course, it's the community version, so it has good amount of free features there. And we are planning to release our first version of DLRT by end of Q4, so basically end of this year. And later on, we're going to expand our support for different type of models, like RNN models or GAN models or the other type of models. I know I'm a bit